So, gravitational field strength. The word field describes how some actions occur at a distance. Okay? So what that means is that a satellite, all right, okay, the moon is in the Earth's gravitational field, so it is affected. It has certain behaviors based on its position. A regular, like, telecommunications satellite is in the Earth's gravitational field, so its behaviors are based on where it's at. We are in the Earth's gravitational field, so we have our behaviors based on our location, i.e. we fall. Okay? So a field describes how some types of actions occur at a distance from the center. Now, gravitational field strength is the ratio of the force at some point in that field divided by the mass of the object experiencing the force. It is the force at some point in the field divided by the mass of the object experiencing the force. Okay? What type of force do you think this is, if you had to label the force? If it's a force in a gravitational field. Force or gravity, right? All right. The variable for this is a lowercase g. What does that mean? What is a lowercase g? Okay, we're not just saying just gravity. Force of gravity is F of g. What's just little g? Acceleration due to gravity, all right? So the gravitational field strength is essentially the acceleration because of a large object. Okay? Based on your position with a large object. Okay? What is ratio? What's the math for ratio? Huh? Dots is one way to do it. What's another one? Think more of a math way of writing a ratio. Huh? Fractions. That's a ratio, right? So let's go here. We'll talk about how this turns out. So it said gravitational field strength, G, is equal to the force acting on the object in the field divided by the mass of the object experiencing the force. So we've seen this before as force of gravity is equal to mass times the acceleration due to gravity. And we can see it over here like this. Force of gravity is gravitational constant times mass of object 1. I'm going to use big mass here. It doesn't really matter, it's just easier than trying to figure out which one's M1, M2. There's no real reason other than one object, two object. So I'm just going to say mass of the big object divided by the mass of the smaller object over r squared divided by the mass of the object experiencing the force. And then so what happens to these two little masses? They cancel out, and that means that G is equal to the gravitational constant times the big mass, all right, basically the orienting mass over r squared. Take a look at your pink sheet. Do you see this anywhere in your pink sheet? Kind of, right? Because you see this on your pink sheet down there, right? And you can tell by where it's located that they're referring to it as the gravitational constant, the universal gravitation, excuse me. So, but they don't actually give you this equation. But y'all are smart. Let me show you. Now you are. I know. Sometimes we have doubts, but it's there. Mass of the big object, mass of the small object, divided by r squared. That is your g. That is your little g. So what are the units of little g? Yeah, meters per second squared. We don't have to worry about trying to find our way through all that g stuff and the m and the r squared. We think gravitational field strength. Didn't we just say that that's acceleration due to gravity? Well, acceleration is g. Is meters per second squared. So our units for this are meters per second squared. So in other words, gravitational field strength is how an object is accelerated inside of an electric field. Gravitational field, sorry, jumping ahead. Gravitate inside of a gravitational field. Okay? Yes?
So that's how we find like gravity with different times?
Yeah. And that's also why, after you'll see that we're going to start, we compare things to ourselves because it's easy and what we know, right? So when you see problems, they might ask you, and and how many G's? So that's basically asking you to figure out what is the ratio, what is the proportionality of one planet to another. You're using G as your basis. Okay? Okay, so that's basically universal. That is basically gravitational field strength. Remember, it's basically an acceleration. It's acceleration due to gravity. Okay? Now, one more term. We're not going to spend a lot of time on it. Okay, gravitational potential. So if we can do gravitational forces, and we're talking about big scale stuff, the same thing occurs for energy. Okay, we can do energy on a big scale. And it comes to find out that energy on a big scale, gravitational potential on a big scale, is G big M little m over R. Okay? Oh, and it is negative.
No, R squared?
Nope, and I'll show you why in just a second.
Well, is that the one I asked you?
I'm not sure. Okay? And that one is on your pink sheet. You'll see that's the bottom one. What was I going to say something else about this? I can't remember. All right, well, we'll go. Oh, yes. Okay. Now, I can't show you a pure derivation of this. That would be all that easily understandable because on the surface of the Earth, right, we kind of accept the fact that the acceleration due to gravity is 9.8. The gravitational field strength is 9.8 meters per second squared. But is it 9.8 meters per second squared all the way out to space? No. So because that G is changing the further out you get, when it changes like that, that is no longer an algebra problem, it's a calculus problem. So that's why I'm not going to go into that derivation. Now I can do this though. If you bring an object in, at its core, work is equal to force times distance, right? So let's see what happens. Force of gravity is G big M little m over R squared. And the distance that you're bringing something in or out, right, is basically your R. So you see why it's over R now? What happens? Those two guys are going to cancel. And we are left with G big M little m over R. That's why it kind of ends up that way. All right. The pure derivation will have a lot more calculus in it, but that's a good place just to start to figure out how it works. We're done. Tomorrow